you're going to do as well then, and the others who are going. So this is then substitute. Substitute. That was the first one, and obviously this is what we've been doing now all the time with the factor theorem and the remainder theorem. Can you see that these things are linked? Then the next one was when you equate, and this is when we say fx is equal to a value. So for instance, equal to 2. So obviously this can form into a equation or a quadratic equation even, or even equating 2 fx and gx. Yeah, and then remember, fx is y. I'm sure you know that by now. Then we did inverse functions. Here we will do a little bit more difficult ones. Look, that is how we write it also. Find f negative 1. You need to know that is the inverse function. And then the last one. Yeah, we'll add it just now, yeah. And then compound functions, which was fg. And it always works from the right to the left. Composite, it's the same. We can write that word as well there. Compound and composite. Composite. Fg, so G goes into F. Okay, now what's extra now is what we call the domain and the range. Now the domain is always your x values. The domain is your x values and the range is then your y values. That's your y values. So you must read carefully. If we ask, find the domain of fx, find the range of fx. Now, can anybody tell me what will happen to the domain and the range on an inverse function? Yeah, they swap. So for an inverse function, the original domain becomes the range and the range becomes the domain. So when we have to draw those graphs, you don't even need to set two tables. You can just swap the values and then draw that graph there, the domain and the range. Okay, now what we also want to add here, let's just add it here, is restrictions. When will we have restrictions for the domain and the range? Now remember, the range depends on the domain. The domain is your x values, that's your independent variable, but the y changes according to x. Now, what restrictions can we have on the domain? I can never ever divide by a 0. That's undefinable. I can never divide by a 0. That's undefinable. Undefined. So for instance, if I have something like this, x over x plus 3, then we can say x is not equal to negative 3. Because if you have a negative 3 there for x, you're going to divide with a negative, which is undefinable. So that's a restriction on your domain. You'll have to add that as a restriction on the domain. And what else? We've said it often. What can you never get? Yes, you can never ever get a negative in a root. So that will be the second restriction on that one there. That's your restriction. So what we can do is they can also give you functions to draw. Most obviously that they're going to do it. Now on higher level, we don't draw graphs on graph paper. You draw a sketch graph, which means, that's the words we're going to use, set a table, choose a scale. You must set your own table and choose your own scale to draw those sketch graphs. That's all that's included here. And then we're also going to look then at the graphs of the functions. Now, let's just add. No, the range depends on the domain. So the restriction will depend on this one. So you can't just give it the general rule here on this one. Okay, now then we're going to look at graphs. And then especially exponential graphs. So you must be able to draw the graphs, but also exponential graphs. Now, what is an exponential graph? This is when we say y is equal to 2 to the power of x. That's an exponential graph. And the typical exponential graph looks like this. We must always put arrows there, label our axis, and where will it cut here? But they were all, y is equal to 3 to the power of x, y is equal to 4 to the power of x. They all cut at the same place. What? Yeah, you're right. So if I put a 0 in here, then it will be the point 0, 1. Because anything to the power of 0 is 1. You can get a fizzer. Okay, so that's the basic exponential graph. And it's good to know how the basic shape is going to look like. If we add now here a +1, obviously it will move up or down, isn't it? And if as this base value changes here, it's just wider or smaller, that will happen to that one. Now the inverse function here looks like this. And this is y is equal to log x. Yeah, log base 2 of x, sorry. Log base 2 of x. That's the inverse graph. The inverse of the exponential is the log one. And then what's also important is it's asymptotes, which means it gets closer and closer to 0, but it will never cut the axis. So you must draw it also like that so that we can see those asymptotes. Asymptotes. So this one will get closer and closer here to 0, but it will never cut it. And then we're also going to meet E and Lin, which are two new friends. So y is equal to e to the power of x. Now on your calculators, have a look there. There's a button on your calculators which says e. It's here on the right hand side. Lin it says lin, and then you have e to the power of x on the right hand side underneath the log button. Can you see that one? It's on a second function, ex. Lin, look at the lin button, and then you'll find it there on the second function. So we're also going to work with e. E is a very special number, and the graph of this one also looks like this. Where will it cut here? 0, 1, because e to the power of 0, you can test it on your calculator, shift ex 0, and it's also 1. Yes. So e is a special one. And then the inverse graph of this one looks like this. Y is equal to ln x. Ln is log base e. Okay, but we'll do that with logs. Yeah, but we'll do, this will come again in with logs. But the question on functions involve that. So this is why I'm showing you also the ln. So that's a new one that we. Okay, so this is the background of functions then that we are going to look at. So you can open your textbooks now on page 97. That's where we start with functions. Now, the first thing that they say there, not all equations are functions. Some of them are relations. Okay, so let's just have a look here. This one will be a function. A function, we say a function is a one-to-one, which means for every x value, there's one y value. If I have the inverse of this one, it's the same. It's a one-to-one. So both here will be functions. But if we look at the typical parabola, what would you say? Is this one a function? Yes. For each x value, there's a different y value. For each x value, there's a different, we call it a one-to-one. It looks like this, a one-to-one. For each x value, there's one y value. But how will this one's inverse look like? Like that. The inverse, if you do it with the table, you'll see it. So that one is not a one-to-one. This one is a relation, because now one x value, let's say for instance that is 2, there are two y values there. Can you see? So the same thing here for the 3 and the 4, there are 2 y values that you have there. So that one is not a one-to-one. So that's the first thing that we're going to look at now. Is it a function or not? And they're going to ask you that, and why? And the reason that you're going to say, yes, it's a one-to-one, or no, it's not a one-to-one. That's what we're going to use. So let's look in the textbooks now on page 97. There you will see, there they start off with a relation. So a function is a special kind of relation where each element of x is an element of y. Right, so on page 98, they're doing that with tables. So look at that one, y is equal to 2x plus 1. For each x value, there's a different y value, can you see? So it's a 1 to 1. An element, that the symbol there is an element of. You didn't do sets. It's something that's now in the new syllabus in again. But that symbol means, the symbol that she's referring to is this one, E, and that means an element of. It belongs to. It belongs to that one. Okay. Then look at example 2 now. Now we have y is more than 2x plus 1. If you look now at all those dots plotted on page 99, this is a relation, can you see? Because there are more y values for each x value. So at the bottom of the page, we have a function or not a function. And what we actually say is we do the vertical line test. So if you place a vertical line here, then there's no place where they correlate. But if I take this one and I do a vertical line test, I've got for each x value more y values. So also one that looks like this, it will be a relation, not a function. Okay, so that's the first thing that we are looking now, just determining that. Page 100. Let's look at those examples. This is out of tables. So for the first one, would you say that one is a function? No, because there's 2 y values. Can you see? There's 2 y values there. Number B, is that one a function? Yes. And then number C? No, because the y values repeat. Okay. Page 101, we're going to do that exercise 26 orally. So number 1, will that one be a function? Yes. For each, it's a 1 to 1. Number 2? No. No, it's a relation. Number 3, a relation. Number 4, yes, 4 will be a function. X may repeat, but not Y. Can you see? And there they come up with that vertical line test that we're going to use. A what? No, a hyperbola is a function. No, sorry, you're talking about a hyperbola. The hyperbola looks like this. No, this one will still be a function. It will still be a function. Yeah, that's so easy, that vertical line test. Okay, so let's turn around. When it looks like that, then you'll get that. Okay, so let's look at this. Then the next one is now on graphs, so we can look the graphs. The first one is a straight line graph, so definitely that one is a function. The second one, between 3 and 5, they overlap. Can you see this hyperbola overlaps now? So that one is not a function, it's a relation. Look at the second one. Okay, number A, is that one a function? Number B, no, it's a relation. C, relation. Look at that. That is absolute values. It's also something that we're going to do now in this following module. So absolute value, no. And then D also, no, it's a relation. E, it's a function. It's a quadratic one and it's still a function. Okay. So now we do exercise 27 orally. Which of the following graphs represent functions? Number 1, yes, it's a 1-to-1. 2, yes, it's a 1-to-1. 3, no. 4, yes. 5, no. No, because there's lots of y values for the 1x value, the vertical line test. And then number 6, also no. Okay, dependent, you know this, that x is the independent variable and y is the dependent variable. Function notation, what you should also just look at, I should have added it in the summary, is on your level, they also use it sometimes like this. We've seen it already. Yeah, but you've seen it last year already also, but I just want to confirm again that this means it's fx. It's just another notation, so it's the same thing. Okay, so there they start there now with substitution, the first one's there, and the examples at the bottom of page 105, but that's what we did last year. And then we come now to exercise 28 on page 106. And this is now where we are substituting. So I want us to do this exercise quickly now, just to make sure that we remember last year's work. And then we're going to go over to this domain and range, the domain and the range. Exercise 28. Okay, so let's mark then this exercise. This is then about substitution and equating. So we have the function fx, which is equal to 2x minus 5. So you substitute the negative 2 in there, the negative 2, and the answer is negative 9. Negative 9. Right, the second one, number B, fp, it's then just 2p minus 5. The p goes in x's place. Number C, ft minus 1, what does that mean? The t minus 1 goes into the x's place. So t minus 1 minus 5, and then I think you must simplify this one. So it's 2t minus 7, then there. Right, the next one, number D, now it's equating. Look at the difference between the two. So 2x minus 5 is equal to 0, which makes x equal to 2.5. Obviously, we're using that a lot of times. And then the next one, 2x minus 5 is equal to 5m. You can play around with that one, but you can't get a solution on that one because you've got two variables. The next one is now number 2. fx is 3x plus 1 and gx is x to the power of 3. So now you have to f2 plus g negative 1. So it's still substitution that we're going to do here. What is f2? 7. What is g negative 2? Negative 8. So the answer is negative 1. Negative 1 for that one. The next one is now the product that we're determining there. So it's f2 times g f2 times g negative 2, which is exactly those two values that you had there. So the answer is negative 56. Negative 56. And then the next one, number C, g negative 2. Now we know that g negative 2 is what? Is negative 8 over 7. That's the answer. And then the last one, gx minus f. So look at this one, gx minus f300. You're just going to do what they say there. This is the kind of question that you're going to get. 10 g2 plus 19. Yeah, there. So here I start with gx, which is x to the power of 3 minus 515. I put it into the original one. Is equal to 2g is then, what is 2g? 2x to the power of 3, isn't it? This is then 2x to the power of 3. And then I multiply it with a 10, which is then 20. Because well, it is G2, it's not 2G. Yeah, sorry. Yeah, sorry. So what is it? 18.
80 plus 19.
And then then you just solve it. So x is equal to, you'll get the cube root of that, 8.85 on that one. So very easy. This is then the first to substitute and equate. Okay, now we're going to look at the domain and the range. It's more now about this domain and range there. Domain is the x values, range is the y values. And they say the one depends on the other, and now we're also looking at the restriction. Now, for most of the time, we can say x is an element of the real numbers. Real numbers means it includes all the numbers. That's especially when it's a line. But from there, you have to look at the restrictions. So if we have something like that, they will say x is more than 0. Or more and equal to 0. You can press your square root of 0, and then you get 0. So that's still included here. And then the other restriction, what we said is you cannot divide by a 0. So the range will depend on the domain every time there. Okay, so let's look now on page 108. We already looked at those ones, is it a function or not. But now we're looking at the domain and the range. So look at the first one. What would you say is this one's domain, Kari? 1, yeah. So x is an element of the real numbers, x. And then what is, it lies between 0 and 5. So we'll write it like that. Can you see? That's the domain. Now look at this one's range. Now we look at the y values. So again, we can say y is an element of the real numbers. You don't need to put it in that set notation. That's not necessary. And this one is -5 is less than equal than y is less than equal than +5. No, I'm at number 1. Number 1, the domain of 1. The domain of 1. No, it's not a function. But yeah. But we're not asking now, is it a function or not? We're looking at the domain and the range. Now look at number 2. What would you say is the x values here, Albert? Look at the picture. Number 2. Yeah. Yeah, the domain. Is there a restriction, Albert? No, there's no restriction. It's arms out. So x is an element of the real numbers. X can be anything. X can be anything. X is an element of the real numbers. But for the y, there's a restriction. So JP, what is the restriction for y? Yeah, but you can't just say -6. Y is more and equal than -6 because it's arms up. Y is more and equal than -6. Right, look at number 3. Right, Joshua, what is the domain here at number 3? What is the domain? Now, look at the x values. -4 is less than x is less than 5. This time 4 and 5 is not included. They're not included. There's open circles. Okay? Oh, this one is solid. Yes. Sorry. Didn't see that one. Leo, what is the range of number 3? Yeah, the range. The range is the y values. -2. Yeah, but less and equal, Leah, to y is less than 5. So that's how the range will look like. Okay, and the last one, number 4. Joanne, is there restriction on x here? No. X is an element of the real numbers. It could be anything. There's no restriction there. And the domain, same thing. Y is an element of the real numbers. There's no restriction there. Okay, restrictions on the domain. This is what I've given to you already, the negative in the root or dividing by a 0. So if we look there at the bottom of page 109, Look at the first one. We cannot have a negative number there, isn't it? So x, what should x be? So what we do here is we actually say that 4x plus 1 should be more than equal than 0. That's the value that you need to find. So 4x is more than equal than negative 1. X is more than equal than negative a quarter. X is negative a quarter, but the root is still then positive. Can you see? The root will still be positive. Yeah, I've removed the root to solve it. Now look at number 2, gx. Well, what restriction will there be on x? X is not equal to 2. It could be anything. But if x is 2, I'm dividing by 0, which is undefinable. Right? Number 3, is there a restriction? No, because it's a square there. T can be any number. If you square it, you're going to get a positive value. So no problem there, no restriction. T is an element of the real numbers. T is an element of the real numbers. And the last one, if you look at the last one, I don't need to look at p plus 2. I just look at the denominator. And there we will say p is not equal to 3. But if we look at the root, what there? P might be? Yeah, so P might be a negative number, then it will be positive, but 1 minus 1 is 0. But we can't have two different values for P, so that one is impossible. You cannot, that's why it's got that star there. That one is impossible to calculate there at that stage. Okay, let's look at exercise 29. So now we're just looking at those restrictions. Let's do it. Exercise 29, page 111. Okay, give the domain of the following relations. Okay, so we're just looking at the domain. If you look now at fx number 1, what would you say? Is there a restriction? Yes, because it's a fraction. So what would be? Come, Joshua, we do it now. What is this restriction? Yeah, we can say x is an element of the real numbers. What is the restriction?
X might not be equal to -3.
No, not 0. You need to find out of this one the 0. So if x is -3, that's when we have a 0 there. Right, now look at number 2. Where will we get the restriction? On the first part? No, there's no restriction, but in that root it will have a restriction. So what will be the restriction there? 3x minus 7 should be more than equal than 0. Two and a third. No? Yeah, 2 and a third. Or 7/3, doesn't matter. That's the restriction. So x must be more than equal than that 2 and a third. Right, number 3. Look at that one. No restriction at the top. What about the root? Okay, so what would it be?
T may not be equal to 1.
Oh, if it's equal to 1, it's still okay, because 1 minus 1 is 0. You can get the 0 in the root, but t must be more than equal than 1. No, it might be 0. Look. Yeah, but you're not dividing. Oh, yeah, eventually you can't divide by the 0. You're right. So t should be more than equal than?
No, just more than 1.
If it's equal, then we have a 0. That's right. Do you understand that one? If we can say it's the 1, but then you are still dividing by a 0, which is impossible. So that's why it can't be and equal to. Right? Now look at number 4. The top ones doesn't matter, the numerators doesn't matter, but the denominators, that's what we're looking for. So what about the first one? and t is not equal to -4. So t is not equal to 1 and t is not equal to -4. Okay. The last one is one that can't work because for the numerator it will be a 4, isn't it? And for the denominator it will be a 3. Okay, so that one can't work out. Can you see? Okay, now they've got real life ones, and now on page 112 we come to mappings. Now mappings is the same thing what you actually do on a graph from a table. So when we have this table here with the values x and y, then this is actually mapping. This one maps onto this one. All that they did now there is they did it like this, and then they say x maps onto y, but it's the same as the table. That it's just words that they are using there. So the input values and the output, the y is your output values, your range then there. So, and this is where we talk about a 1 to 1. Look on page 113. If x is equal to 2x plus 1, it's a 1 to 1. For each x value, there's one y value, 1 to 1. Look at the second one. Now, the first one will be a straight line graph like this. The second one will give you a parabola, y is equal to x squared. Can you see now there are many to 1. Many x values to one y value, but it's still a function. It's still a function. Yeah, many to 1. But you don't really need to know all that. The one that we're going to use is 1 to 1 or not 1 to 1. So you don't need to worry about the others because it's confusing. Some of you are very confused. On page 114 there we've got the sine graph. We've got a cubic equation, and we can see all of them are still functions. That straight line test is the very easy thing to use in there. If we look on page 30, and again we're going to do this one orally. So look at the first one. Would you say that one is a 1 to 1? Yes, page 114, exercise 30, number 1A. 1. So that one is a function, so that one is a 1 to 1. Right, number 2. Yes, that's a function, 1 to 1. Number 3, no, relation. Okay, because there are more y values there. Number 4, no. Number 5, yes. 6, yes, it's a function. It's a function. Okay, there's number 2. There they come up with a mappings again. The first one is obviously 1 to 1. Can you see that? The second one, 1. No. Yeah. No, that one won't work because y's got more than one value. 3 is so confusing, I can't even see what's going on there. Also, no. Yeah, no. And then look at the pictures at the bottom. 3a, is that one a function? Use the vertical line test. Use your ruler to test. And number B, no, not a 1 to 1. C, yes, a 1 to 1. D, no, not a 1 to 1. Okay, and there you can see we have finished that first. Shouldn't the bell have rang already? I think you must just, well, you go and ask them quickly. I enjoyed it because we completed a whole chapter now here. Okay. Oh, there it is. But it's very late. Yeah.